Welcome everyone to this course. Now let's go to the next paradigm in machine learning, which is called unsupervised learning. See, at the onset I should tell you that I am not a big fan of these nomenclatures, okay. But anyway, so it exists in some algorithms are categorized under unsupervised learning, so I will have to just talk about it that way. Now again, remember what we did in our very initial classes. So we have samples drawn from an underlying unknown distribution and we are trying to estimate the underlying distribution. That problem remains, so it does not change, okay. Now even for generative models that problem remains, but there is one other angle added to that problem, that we also need to sample from the underlying distribution. So far none of the algorithms that we have seen are capable of sampling. So if you train a neural network, it's only, or rather I should actually, to be mathematically completely precise, these algorithms are not designed to sample from the marginal distribution, they are designed to sample from the conditionals, that too conditionals of labels given data, whatever variable we are calling it as label. Have I mentioned it to you? I mean, I say this always in my first class of generative models, that all models are generative because even the so called discriminative ones are sampling from P of y given x, right. So anyway, so I mean typically in the literature the ones that sample from P of x given y are what are called as generative models, right. But the problem of sampling from the underlying distribution, or rather estimating the underlying distribution given its sample, does not change. This is the one holy problem of ML that is common across all problems that you encounter in ML, okay. Now then what is unsupervised learning? To me it is still distributional learning. The only thing is, right here, estimate the marginals or not conditionals. So given, so D that is sampled from xi, so this is the foundational problem of unsupervised learning. Go back to the philosophy of ML. If we can see one data dimension or label as one other extra dimension of data, right, then the paradigm merges, right? So we just, we are not doing anything. But typically in supervised learning, you take away one dimension of data and force that and call it as a label, okay. Unsupervised learning in English language is label free learning. But if you take the language of mathematics, it is still distributional learning. You estimate the marginals, that is it. It is not the conditionals. So that way you do not have labels, you see. The point is that you do not have labels here. But you can debate what labels mean. I can always call one of the dimensions or a few dimensions of data themselves as labels, right, and estimate the conditions. By the way, if I take a few dimensions of data itself as labels, okay, and estimate the conditionals or marginals, people call it in a different name, by a different name. It is called self-supervised learning. We will see some algorithms for that as well. But ultimately what we are doing is distributional estimation given samples. Does it make sense? Now the question is, what changes? Nothing changes actually. We still have the same KL minimization and we still have the exact same ERM that we do, okay. But the so called loss functions that we define, now remember in supervised learning the KL divergence that we were minimizing was between the true conditional and the model conditional. And this p theta of y given x, we approximated this with multiple parametric functions, looked at linear functions and nonlinear functions and neural networks and whatnot. Ultimately this scale divergence is what we call as loss function, right. In the ERM world, if you write down this scale divergence, it will become a loss function. Now in unsupervised learning, the KL divergence that we will be optimizing will be the marginals between the true marginal and the model marginal, that is it.
Will it still be called the loss function?
Yeah, you still call it the loss function, right. So, what distribution do you choose is very different, that is it. Okay. So, now here you do not have labels. Okay. So, this is one thing. The other point that I wanted to make is in most of the unsupervised learning algorithms, right. So, P theta of x, which is the model distribution, in unsupervised learning So, if someone asks you what an unsupervised learning algorithm is in some interview or something, please do not tell them that it is estimating the marginals through KL minimization. Tell them that it is learning without labels. Okay. So, model distribution in unsupervised learning is taken to be a latent variable model. This is the typical choice. So, typically you make your p theta of x to be equal to, express that as the marginal between the joint distribution of p of x and z, where z is your latent variable. Okay. This z, okay, we will come to that in a while. Is this clear? When you see, the problem in unsupervised learning is to estimate the marginal. Okay. Express the marginal as a latent variable model, either this or this, depending upon what the choice of your latent variable is. Express that as a marginal over an integral or the sum over the latent variable. This is a typical choice. Okay. Now, the question is, why do you want to estimate the marginal of p of x? In supervised learning we can understand, right. We want the labels of data, finally we want to predict the labels. Now, what we want to do is infer, which is estimating p of p theta star of y given x test. That is what we need to do, that is our inference. In unsupervised learning, what do we want to do? Why do we need to estimate the marginals? So, in one use case we would want to estimate the marginal because we want to sample from them, which becomes the generative models. But here we are not talking about the sampling procedures yet, we are only talking about implicit estimation of the marginals. Why do you want to estimate the marginals?
Some patterns.
Of course, data reconstruction is one thing, the other thing is
Patterns.
What do you mean by that?
So from
That is a good answer by the way, but you need to define what a pattern is.
how exactly it looks geometrically, like are the points like in a way clustered in some way?
I mean, I have not defined what clustering is and all that, right. Anyway, so okay, so they call it as data exploration. So, you need to explore the data. Okay. Why do you want to estimate the marginals? Because you need to explore the data. So, what do you mean by that? How does it translate to mathematically is the question. Okay. Here is what my answer is, right. Typically, it is modeled as a latent variable because now once we have a latent variable model, we can estimate p theta of z given x. If we can estimate the marginal of data as a latent variable using a latent variable model, okay, we can perhaps estimate the posterior of the latent variable conditioned on data. Okay. Now, why do we have to do this is the question. Now, suppose z is a discrete variable. Suppose z is a discrete random variable. Okay. In that case, what does this posterior tell you? For every x, okay, you are getting a distribution over a discrete random variable. Now, let us say that we take z to be 10. It's a discrete random variable, okay, and how many choices that discrete random variable, what I meant by z to be 10 is that it's a discrete random variable that can take 10 values with certain probabilities, okay. Now for every data point x, I get a distribution over 10 dimensional discrete random variable. So how do I interpret that? So one possible interpretation is that I am grouping my data into one of 10 categories, and this is what is called as clustering. So clustering is nothing but estimating the posterior of a latent variable model, the posterior of the latent variable given data under the assumption that the latent variable is discrete. So this makes sense. This is called clustering. So I don't understand English, I can only understand math. Do you see what is happening? So now suppose we choose it to be a discrete random variable and estimate a latent variable model, okay, and then estimate the posterior of the latent variable given every data point. What you are actually doing is grouping every data point into one of 10 categories using this latent variable. Now if you are getting the entire distribution on a latent variable for a given point, how is it grouping? It is soft grouping. If you associate that data point to the one with the maximum probability, then it is hard grouping. So one is called the hard clustering algorithm, the other is soft clustering algorithm. We will see examples for both of them. If you can connect the dots, we have already seen a latent variable model earlier, which is a Gaussian mixture model. In a Gaussian mixture model, we can actually find this p theta of z given x, and that is why GMM is used for clustering, okay. Now if z is continuous, not discrete, okay, then estimating samples of p theta of z given x is called representation learning or feature extraction, because for every x, okay, in fact it is not, you need to actually, strictly speaking, you need to sample from this distribution, because for every x you have to get one z. Let us say that we take that z which corresponds to the mean of this distribution, the peak or mode of this distribution, then for every x we are getting one z that has the pattern or the compressed version of the data. So these are called this is called feature extraction. So as a side fact, I have named my research laboratory as representation laboratory. One, because rep lab seems funky. The other thing is that all I want to do is do an unsupervised learning. Learning without labels is what I am interested in, right? And what is learning without labels is try to learn a latent variable model, okay, such that the posterior of the latent variable given data gives you a good representation of data. That is it. That is why we have named our company also as Latent Force, because all we are trying to do is to learn representations of large scale data so that the downstream task becomes easier. So now how do you use the z is the question. Okay, fine, you estimate the marginal, you get a z, then what? You can use that with labels for your downstream tasks. Instead of using an image, suppose you do some unsupervised learning, okay, where you can estimate the representation of the data point. You can use z as vectors and then build a classifier on top of it, and so on. So got it? In fact, again, a bit of self-marketing. One of the biggest value propositions that we are doing in our company right now is that we provide very good z's such that your downstream task is more efficient. That's the story that we are saying. Okay. Please note that we are still not talking of sampling. We are still talking of estimating the marginal and getting the posterior of the latent variable given data. Okay, let me write that down once. Okay. Now, if z is discrete, then it will become clustering. If z is continuous, this will become feature extraction or representation learning. Oh, by the way, this has another name. These are called embeddings also. Embedding, feature or representation extraction, right? So all of those are the same things. Okay. Any questions on this?
When we have discrete variables, we can see this also as a representation of discrete.
Discrete representation is what is called as clustering.
Instead of seeing it as like grouping it into say image of a few dimensions compressed into discrete images.
Agreed. So, but the thing is, when you have discrete representations, all you are saying is which probability, something it belongs to this particular group with probability. See, what happens is, if you choose Z to be continuous, it may have some implicit semantics embedded into it, because distance metrics etc. will make sense. But if you are looking at discrete spaces, those values that these discrete random variable take may not have any embedded implicit semantics into it, no, because you are looking at a discrete space. I mean, you can look into a discrete random variable as a one hot vector at higher dimensional space, right, because you can represent every discrete random variable as a one hot vector. In that kind of a space, distance metrics do not make any sense at all. So, it is mostly looked into as a grouping thing, but I agree with you. We can still look into this as a feature. So, given a data, you are saying, oh, okay, you can represent each of the data point using a long one hot vector. Okay. In fact, if you make it a one hot vector, then it becomes hard clustering. If you give the entire distribution over Z, then it becomes soft clustering. That is what people refer to as. So, when you tell people that you are doing unsupervised learning, they are saying you are doing clustering. I mean, what is clustering? It is basically estimating assuming that your marginal on Px or marginal on your data is a latent variable model, and estimating and assuming that your latent variable is discrete, and estimating the posterior of the latent variable given data. This is clustering. Yeah. That is a hyperparameter. The number of clusters and features are hyperparameter. It is exactly the same as the number of Gaussian mixtures that you choose in a GMM. That is exactly the same, which is a hyperparameter. Okay. In fact, in the coming classes we will see that the so-called k-means algorithm, okay, is a special case of GMM with a certain assumption on the variance of the individual Gaussians that we do. We will see that. Come again? Oh, good. Yeah. He is saying that it is completed in tutorials already, but nevertheless I will mention that here. Any other questions on this? So, in the next classes what we will do is, we will look at a few representative algorithms for unsupervised learning. Specifically, I will talk about principal component analysis, PCA, which is again assuming that Z is continuous, okay, and solving a particular optimization problem, and under linear models. Okay. Oh, I should tell you, I should draw another connection here. See, just like there is a one-to-one relationship between ERM's view of supervised learning and the probabilistic view of supervised learning, the exact same thing applies here. For instance, I will talk of an algorithm called principal component analysis that makes a particular assumption on the model and or computes a loss function and tries to find a Z. This is done in a completely deterministic way, not the probabilistic way. Now, one can show that doing PCA is equivalent to minimizing the KL divergence with a particular assumption on P theta of x. Okay, exact same connections apply. See, as I said, no, the principle wise nothing has changed. The only thing is that we do not have the so-called label random variable here, but the underlying algorithms are the same. So, we will look at principal component analysis, and also look at, I will talk about this class of algorithms called autoencoders, okay, where instead of using a linear model for loss for the underlying model, you use a neural network. Okay. And we will look at algorithms such as GMM. We have already seen that. I will talk about that as well. The other algorithms, class of algorithm that I will be talking about is these class of algorithms called self-supervised learning, which is again the same thing, but there you take some of the dimensions of data. See, here in so-called unsupervised learning, we estimate the entire marginal. In self-supervised learning, we estimate a conditional. The conditioning is over a few subset of the data dimensions conditioned on the entire data. If we estimate some of the subsets of data dimensions conditioned on the entire data set, then they are called self-supervised learning algorithms. In supervised learning, you take another random variable, call it label and estimate P of y given x. In unsupervised learning, you estimate the marginal. In self-supervised learning, you estimate the conditional of a few dimensions of data conditioned on the entire data. That is exactly what is being done in GPT etc. I mean in GPT etc. there is one way to train, which is called masked auto encoding, right, where you take some subset of data, mask it and try to reconstruct it back. We will look at all those kinds of algorithms in the coming classes. Okay. Any questions on this? The overall philosophy of what unsupervised learning is? It is learning without labels. Okay. So on that note, we will stop today. We will meet you in the next class. Okay.